All right, so we had finished deriving this equation for the growth of perturbations in an expanding universe. I should say that what we're doing, though, is since we have not included pressure in this derivation, that must mean that this could only be valid for wavelengths that are for modes, if you like, Fourier modes, or perturbations which have a size that are very large compared to the gene's length. So let me just say this is good for wavelengths or sizes of perturbation that are bigger than the gene's length. But that's good, especially when the gene's length has become very small. Then it's sort of this equation is good to use. Okay, so there's some examples that we can do as laid out in the book, and we're going to do these live, and you're going to see me struggle with math perhaps. Let's do example. Example number one, which is that the matter component of the universe is very small. What does this mean? So if omega matter is much, much less than 1, we will ignore that first term. This would be, for example, during the radiation-dominated portion of the universe, so rad-dominated. Okay, so let's see what we get. We get a delta double dot plus 2h delta dot, and that's approximately equal to 0. We want to solve for delta, so we need to know what h is. Okay, well, h is a dot over a, and when we're in the radiation-dominated phase, we have that a of t is given by some t over t naught, approximately, to the 1/2 power. Not so hard to show then that if a goes like t to the 1/2, that means a dot over a, that just looks like 1 over 2t. So in that limit, delta double dot 2h is apparently 1 over t times delta dot, and that's approximately equal to 0. And whenever I see an equation like this that has, there's no 0th order derivative, it's a double derivative and a single derivative, you might consider writing f, as delta double dot, so that f dot is delta double dot. Then this equation can be written as f dot plus 1 over t times f. And that may be a slightly less scary equation to try to solve if you want to. Let's try it. Let's guess that f is equal to some constant times the power of t. I'll just call it a times t to the p. And if that were true, then f dot would be a times t, a times p to the t to the p minus 1. In other words, probably also good to write this as this is just simply p divided by t times f. That might work. So now let's plug it on in. What do we get? We get an f dot is p over t times f plus 1 over t times f equal to 0. And, you got t's canceling, assuming that t is not equal to 0, and f is not equal to 0. That apparently means that p plus 1 must be equal to 0. In other words, p must be equal to minus 1. And so we've learned that, what have we learned? We've learned that delta dot is equal to some constant times t to the minus 1, or it's equal to a over t, and now we can simply integrate that to get delta. That would mean that delta would be, I suppose you'd have to integrate that, and so you'd have something like an a times a natural log of t over some t naught plus some constant which you could always absorb. How is it in the book? Okay, there's basically two constants, and the way I've written it, you can basically you can write them as a and then t naught, and you could feel free to write them in terms of b1 and b2. But basically what you see is that when the matter is a small component, when you're dominated by radiation, you only get logarithmic growth in your densities. So that's slow. Logarithms grow quite slowly. Okay, and that's one example. The other example I suppose it looks like cosmological constant domination. Is that right? Da, 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 da. Example, I'll do lambda dom. And in this case, the scale factor goes like an exponential, and in fact, it does look like the Hubble constant times t, and it's literally, it is a constant. You can check this, by the way, because a dot is equal to h e to the ht, and if you divided this by a, which is simply e to the ht, then you simply get h. So that's all legit. Okay, that means that our equation from above, master equation, delta double dot plus 2h, just a constant. And again, if matter is subdominant, which I think is what we're assuming, yeah, it is. Huh, how do you like that? Delta double dot plus 2h, where h is a constant, times delta dot equal to 0. Should we play the same game that we did before? You could. Yeah, I'll do it. Why not? If this is f and delta double dot is f dot, then apparently we have f dot plus 2hf equal to 0. I've seen an equation like this before. In fact, I'm going to take this to the other side and let this be equal to minus 2hf. Yeah, that's one of them exponential things, ain't it? Yeah, I've seen one of them before. Okay. In fact, you could integrate this. Yeah, let's do some integration. This is df dt. This is my favorite thing. Minus 2hf. Yeah, okay, take this over there. df over f is equal to minus 2h dt, and integrate from some initial time to some later time, and you're going to find ln. You're going to find ln of, I don't know, f over some initial f is equal to minus 2h t. Hey, that's what the answer is going to look like. Apparently f, you got to exponentiate both sides, of course. F naught times exponential of minus 2ht, and then you have to integrate this once to get, right, this is what delta dot is, so you have to integrate this once. Apparently that means that delta as a function of t, you'd have this term plus some constant term, and that's what I see here, so I'm going to write it the way that Ryden does it. c1 plus c2 e to the minus 2ht. Wow, that was exciting. Lastly, I think we need to do what happens when you have a matter-dominated universe where omega m is equal to 1. Example. Omega matter is equal to 1. And by the way, that also means that the scale factor goes like t over t naught to the 2/3. And that means that the Hubble constant is equal to simply 2 over 3t. Verify that. All right, our equation, delta double dot plus 2h delta dot. Oh, what is that term? I already forgot. Whoop, whoop, whoop. Minus 3/2 h squared omega m delta. Minus h squared omega m 1. In other words, delta equal to 0. Is that the right term? And if h is equal to 2 over 3t, that means that this is 2, blah, blah, blah. So that's 4 over 3t. Check the book. Yep. Delta dot minus 3/2 times a 4/9. I'm not that smart enough to do that in my head. 4 over 9. T squared in the bottom. And the 2, so you get a 3 on the bottom and a 2 on the top. That's right. 2 over 3t squared. Is that right? Yeah, I'm smart. Okay. Delta equal to 0. All right, and then it's your task to solve this equation, and it looks like we do a simple, there's a name for this. Oh, the Frobenius method, more or less. You could write down a series solution, but we're just going to, let's guess that this is equal to some a times t to the p, which means that delta dot is equal to p over t times delta, and delta double dot, so you bring down a p, you bring down a p minus 1. I think that means that this is p times p minus 1 over t squared times delta. You can check that. So those are the things that we'll jam on into our equation here. So apparently we have a p minus 1 over t squared times delta, plus a 4 over 3t times a p over t times delta, and then minus 2 over 3 t squared delta equal to 0. And if t isn't equal to 0, if delta isn't equal to 0, then we're in good shape because all the deltas go away, the t squareds go away, and it looks like we have a simple p times p minus 1, plus a 4/3 p minus a 2/3, and that's equal to 0. Cheating, cheating. Yeah. All right. And, well, apparently there's a quadratic equation here. You would find that p is apparently equal to a minus 1 or a plus 2/3, and that is exciting. What you apparently find is that the overdensity would evolve like this. It would have one term, I'll call it d1, times t to the 2/3. That's the growing solution, and there's a decaying solution as well that goes like t to the minus 1. Remember that we're in this limit when t grows like t to, the scale factor grows like t to the 2/3. In other words, this here is really proportional to prop 2, the scale factor as a function of time. So, you got a decaying solution, you got a growing solution. The growth occurs, delta of t is proportional to the scale factor, which, as is pointed out, also proportional to 1 over 1 plus z. Good. So those are the 3 different kinds of universes you could live in: radiation dominated, cosmological constant dominated, matter dominated. And you see that you really only get significant growth when you are living in a matter dominated universe.